Hello everybody, I'm Coleman. I do testing and customer support at Kinarm, and this is my talk about my experience programming the Coherent sample task. This is the first full experiment I programmed, making all the parts like state flow and visuals, and I discovered some things along the way. Things I'll go over in this talk: a very brief overview of the task, how I designed the state flow, and troubles I ran into. Mainly having to make repeat target V codes, managing my TET, and monitoring video performance of the Kinarm. The task. You show the subject moving dots. Some dots are moving in the same direction, right or left, with the same velocity. Those are called the signal dots. All other dots are moving in random directions with random velocity. Those are called the noise dots. Every time you draw a frame of movement, the number of signal dots stays the same, but which dots are signal dots, which are noise dots, changes randomly. At the end of the task, the subject has to guess which way the signal dots are moving. So there is a target to get the subject started. If they enter it, they will see moving dots. Once the dots are done moving, they're presented with a choice. If they answer correctly, the target turns green and otherwise is red. Here's a quick overview of what the task ended up looking like. Trial control manages the flow of the task. It has outputs here to a subsystem called button subsystem that controls the button. And then otherwise, the moving the dots function is the other big chunk of code, and that draws the dots and moves them around. Found what has worked for me when building state flow diagrams is usually working with pencil and paper to determine the states. A good way to find out the states is to make some storyboards or PowerPoint slides about what the subject sees and what happens from moment to moment. Before doing that, here's a helpful sketch that I've made to show me what elements I'll have and what a good position for them is. I like having things down on paper because it helps clear my head. So here's the storyboard of the first state. What is it that is showing when the task starts? What does the subject see? If there are forces, what forces are activated? In this case, there's a button that shows up. So I drew that. Even though it's simple, I think it should be illustrated so that I can recognize it explicitly as a state. So when the subject reaches start, we go to the next step. Here is the next step. Again, simple diagram, but it is helping form the logical progression. At all times, I am defining what the outputs to visuals and forces are. When the dots are done doing stuff, we arrive at a state where we show new targets and wait for a logical condition. Based on that logical condition, we'll change colors on a target. Eventually, I like to draw a state machine diagram. It's an easy way to show me what the state flow should look like and where the arrows can go. So we start in an initialized state. Then we go to show a start target when the task starts. When they reach the target, we go to a state where the dots do things, and then after some time is a transition condition. We go to a state where we ask the subject the direction the dots were moving. If the subject picks incorrectly, we tell them they are wrong. Otherwise, if they pick correctly, we tell them they are right. Either way, after showing the message for some time, the trial ends. And if there are more trials to run, we go back to show a start target. Otherwise, the task ends. Here is the final state flow chart. In the top right, you can see the initialized state where everything is off. In the show home button target state, I grab information about all the variables I need from the TP table and I turn on the start button. After they reach the button, I turn off the start button and I set an output that will tell the dot drawing code elsewhere to start drawing dots. After a bit of time, the dots get turned off and I turn on the two targets to ask the subject what they thought was the direction. Depending on their choice, I will turn one of the targets green or red. After giving the subject 1 second to read the color, I finish the trial. Now that we have made the state flow, we have to draw some dots. So, a quick recap of visuals. To get the Kinarm to draw something, you have to send it a 70-element vector that we call a V-code. Show target block family will generate the 70-element vector for you for many target types based on values you set in the target table. Not all target types can be generated using the show target blocks. That includes repeat targets, path targets, and polygon targets. If you want a dynamic target that changes properties like position, color, etc., you have to modify the V-code yourself. Well, I first panicked when I had to make a V-code. 70 elements is a lot. But then I realized I didn't need to worry about all 70 elements, and I held on to that fact like a very soft teddy bear. So to start making a V-code, you open up the Creating Custom Task Guide and go to the reference chapter 14 and find these tables. Table on the left asks you which target type you want to draw, and then tells you which vector indices you need to worry about. For example, to make a circle, you only need to set 9 numbers at most. After you know which indices to work with, you look them up in the table on the right, V-code vector format. So to see what index 1 needs to be set, you look here at index 1. If you want a circle, put a 1 in this vector element. If you want an ellipse, write a 2, and so on. For V-code 2, write a 0 if you don't want a target to show. If you want it to show on both screens, write a 1. And so you read the rest of the table to build the V-code you want. Let's look at an example. Let's make a circle. Here is a list of indices we need to set values. We'll start by making a 70-element vector of zeros, and we'll set the indices we care about. We'll call the vector circle. Circle 1. We want to have a circle, so we write a 1 here. Circle 2. We want this to be visible to everyone, so we write here a 1. Circle 3 and 4 are the x and y positions. This is in global coordinates. For x, I'll put it in the middle of the screen, which is x equals 0. For y, 30 centimeters away from the subject is close to middle, and that's good enough for me. Circle 5, we set the color. There's different ways to convert a color you want into an integer here. I'm not going to go into them, but I know 255 is blue, so I'll make the circle blue. Circle 6 and 7 have to do with stroke or outline of the target. I don't want that, so I'll leave them at 0. Circle 8 has to do with something called background codes. We don't recommend people use them anymore, so I'm going to ignore that too. Circle 9 is the opacity of the target. I want the circle to be opaque, so I write a 100 here. Circle 10 is the radius of the target, and I'll make it 10 centimeters. That's it. That's drawing a circle in the middle of the screen. And here's a picture of what this V-code looks like on the screen. Okay, but I need to draw hundreds of circles. Here is where I started to hit some boundaries. You can send a maximum of 200 V-codes. A repeat target V-code lets you show a single target in up to 25 different locations, which makes for 200 times 25 is 5,000 maximum targets, which is good for making dots. All you have to do is keep track of the X and Y locations, which means for each V-code I need to keep track of 50 numbers. And 50 times 200 is 10,000. So in my code, I have to manage a matrix that has 10,000 elements. That will make me run into a different boundary. I will run into the TET. TET is short for task execution time. Here is the definition of TET I got from MathWorks website. It's a measure of how long everything, all functions and blocks in your model take to execute once. Because in a real-time system, in each time step, everything gets executed once. And a Kinarm, your TED needs to stay below 250 microseconds because a Kinarm task runs at 4 kilohertz, 2 kilohertz for MATLAB 2013A or earlier. If your task cannot execute everything in it in 250 microseconds, you have broken the hard real-time requirement. It means you are asking too much of the CPU and it can't keep up. The error that you get when your task can't run at 4 kilohertz is CPU overload. Next error, you get told that there's a CPU overload. But if you look over on the screen connected to the robot computer, you'll get some more information. Here's the picture of what a Simulink real-time screen looks like when there is no error. The average TET is up here in the top right corner. While the average TET is useful, be aware that TET is a noisy value, and so it has peaks and valleys. And the average TET may be below 250 microseconds, but if the TET peaks once above 250 microseconds, you will get a CPU overload, letting you know that your model cannot continue performing in real time. Here's a picture of what the screen looks like if you have a CPU overload. A nice red bar at the top tells you that there was an error and the task is stopped. Most people will never see this error. We've tried to make sure there's more than enough TET for people to make experiments with. But since the code lets you write anything in there, you can make yourself CPU overload. Here are some easy ways you can run into it. Operations with big matrices that have hundreds of elements, nested loops. The compiled Simulink real-time code is C code, not MATLAB, which means that there's no vector operations. So the code on the left, A equals A plus 1, if A is a 10-element vector, is this same execution as on the right, which is a nested loop that applies. It's a 10 by 10 matrix, and if you are in MATLAB, if you do the code on the left, it will be faster than the code on the right. It won't just do element by element assignment, but that's not true in C. So if you write the code on the left, know that in Simulink real time, it is equivalent to the code on the right. How to deal with CPU overloads. Sometimes it's one function or operation that is using up a huge chunk of time, but other times you have to find efficiencies in multiple places. The other solution is that some blocks don't need to be run at 4 kilohertz. You can tell the model that some parts can have more time to execute. This is usually a reasonable request for V-codes, as the subject display only operates at 60 Hz or 120 Hz. So I solved my CPU overload problem by setting my dots function to a sample time of 20 milliseconds. The colors on the blocks and the lines in the model indicate what sample time things are running at. So usually the red signifies things that are running at 4 kilohertz. With all this power to draw thousands of targets of arbitrary size comes some responsibility. It is possible to draw targets on the subject display that will drop frames. Big moving targets having lots of targets, such as more than 500. Check your video performance using the video frame interval time. Video frame interval time is equal to the time the target was drawn minus the time target was sent to the process video command. For 60 Hz monitors, it is about 16.7 milliseconds. For 120 Hz monitors, it is about 8.3 milliseconds. Again, most people won't need to care about this, but it is a good habit to check the video frame interval time in your collected data just to make sure that you aren't dropping frames. It's easy to check. You can view it in Dexterity Explorer. In all Kinarm data files, you will find the video frame interval time in the bottom of the derived channels, sources that could drop frames. Running Chrome or other programs running in the background while you are collecting data, using Alt-Tab to switch between windows. For this task, I found that at about 1,000 to 2,000 dots, I'd have frame drops and the video would stutter. I also found increasing the dot size lowered that limit. big targets are more likely to drop frames because they need more rendering time. So I can't give you a hard and fast rule about what that limit is. My advice is to watch the task perform. You probably will notice frames dropping. See the video stutter. And if you have any doubts about whether you might drop a frame, run the task a few times and watch your video frame interval time.